Now that we know how to find the formation equations, let's figure out how to use them as a shortcut, which is always nice to have some shortcuts, isn't it? So if we would take an ordinary chemical balanced equation, let's just take, why not take propane gas, like is in your gas grill, and let's burn it in some oxygen. Okay, so oxygen gas, and then if our burners are adjusted correctly, we should only get carbon dioxide gas and water as a gas coming off of that. And then to balance it, let's see, we have 3 carbons, we need 3 carbons, we have 8 hydrogens, that means we need 8 hydrogens over there. This gives us 6 oxygens plus 4 oxygens, so that's 10 oxygens, so we need a 5 here. All right, now we're balanced. If I want to be able to predict the delta H of reaction of this, remember Hess's law says that we can just add up a bunch of component equations and find that, right? Well, I could search around for component equations that have propane in them and have carbon dioxide in them and have water in them and try and find things that would add up to make this equation. Or I could do a shortcut by looking at those delta H's of formations that we just talked about in the other pencast and find out, we could say, well, if we were making propane from its elements, we'd be making it from carbon and hydrogen. Oxygen is already an element, so we're not making it from anything. You know, there's the delta H of formation of that would be 0. Carbon dioxide, so if we made it from its elements, it would be made from carbon and oxygen. Water from its elements would be made of hydrogen and oxygen. So we could say carbon plus hydrogen makes C3H8, and of course we would have to have 3 of those. Those come in pairs. We'd have 4 of those. We use graphite. We'd use a gas here, and that would be a gas, right? Then the other compounds we have in here, we have carbon dioxide gas. We would make that from carbon, of course, is graphite, only have 1, plus an O2, we only need 1 of those, and there we go. Then we would have water that we need to deal with, that also is a gas in this case. So we'd have H2 gas, that's the naturally occurring state for hydrogen, and O2 gas, that's the naturally occurring state for oxygen, and because we only need 1 atom of that, we'll put a half there. Now, those are the formation equations. But when we do this, this shortcut thing, we don't really have to write these down. I just wanted to show them to you to say, if I would flip this, right? If I would flip this, and if I would multiply times 3, and if I would multiply times 4, everything would cancel. It'd be pretty neat. So we could do that. We could add them all up and blah, 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 get our target equation. Because we're doing formation equations here, and everybody on the left, all these guys on the left are all elements, right? We made them out of their elements. They're all in their naturally occurring states, so every one of them will be 0, 0, 0, 0, 0, 0, 0. So they just all drop out anyway. We don't have to add up their delta H's. So here is the shortcut for delta H of reaction for this guy. Delta H of reaction for our first equation for our propane burning to make carbon dioxide and water, right, is going to be the delta H of formation of the products. Okay, we're going to make them from there. We're going to, in our target equation up here, we're going to make 3 carbon dioxides, right, and we're going to make 4 waters. So let's take 3 times the delta H of formation of carbon dioxide gas. Let's take 4 times the delta H of formation of water, and make sure you put gas, because we're in our table, in our thermodynamic table, when we look this up, there's a value for gas and for liquid for water, so we got to be careful. Now, back, if we were doing this by adding equations, we would have had to flip this equation here, which is for the formation of propane, because we're not forming propane, we're busting up propane. So if we flip, what do? We subtract. And the coefficient for that is 1, so we don't have to put a coefficient in front of it. So we would subtract the delta H of formation of propane. So if I go into my thermodynamic table, I would take 3 times, now let's look up carbon dioxide, and what you've got to look for is carbon dioxide. Now there's 2 values for carbon dioxide for the delta H of formation. Got to be careful that you get the gas, not the aqueous. It's really important, they're not the same value. So we're going to take 3 times negative 393.5 kilojoules, negative because we get energy out when we make bonds. When we make carbon dioxide, we're making a lot of bonds. Plus 4 times, and then water as a gas. Now water, you got to think, well, is water going to be listed under hydrogen or under oxygen? So you can look under hydrogen and see there's not very many things entered there. So they must consider oxygen to be the main element in that we have to look up in water. So then we flip to page 822. On the next page, we find water as a gas and as a liquid. Be careful to get the gas value. And that's negative 241.826. And of course, that's kilojoules per mole. I should be putting per mole here. Per mole. And this is 3 moles. And this is 3 moles. So you can see that the moles are going to cancel out. Minus delta H of formation of propane. And propane is probably back under carbon, so let's go back there and see if it is. And of course, there it is. We have negative 105 kilojoules. And if we want to put per mole, we can, because really this is all times 1 mole. And then the moles will cancel out. Okay, moles are gone, moles are gone, moles are gone. So you end up just with kilojoules. So if we do this, we get negative 2043 kilojoules. We have to cut that off at the kilojoule. We can't have any decimals because of our propane guy, our negative 104 kilojoules. There's no decimals there, and when we add things, we have to cut off at the decimal place. So negative 2043 kilojoules. So that's a fair bit of energy, which is exactly what you think when you burn your gas grill and you burn propane. You should expect to get energy out, and a fair bit of it. So it makes a nice fuel for cooking your steaks or your red peppers or whatever it is you're going to cook on your grill. So let's go back and summarize how we do this. Delta H of reaction is equal to, and here's a nice symbol from math, the sum of the delta H of formations of the products. Okay? And we have to remember that that's multiplied by their coefficients. Each one has to be multiplied by its coefficient. Minus the sum of the delta H's, and of course they're multiplied by their coefficients too, whatever they are. Delta H of formation of the reactants. Because if we were to go back and do this whole thing where we add up all the equations together, we would have to flip the formation reactions for all of the reactants. That's why we have this negative sign here. And you can either add them all up in a parentheses, or you can subtract and subtract them from all the rest of the products, or you can just subtract each one. But this little thing right here looks kind of complicated, but actually it's pretty easy. Take each of the products, look up its delta H of formation, multiply that number by the coefficient, add the next product, multiply it by its coefficient, and just keep going for the products. Then subtract out the same thing for the reactants, and you're done. You've got the delta H reaction. You don't have to add up any component reactions. You can just look it up in the table, and you're good. I'm going to write that page number down here. Page 820 is your friend. the thermodynamic values. We're not going to use the delta G's and S's in that table, by the way, until second semester. So if you're wondering what the delta G's and S's are doing there, they're just they're lying in wait for you for Chem 112. At the moment, in this semester, all we're going to use is the delta H's. So this is how you use delta H of formations to find the delta H of reaction.